Welcome to my channel, RAVIKUMAR Academy. This is a lecture series on single variable calculus. In this lecture, we are going to learn applications of Lagrange's mean value theorem. We will solve a problem related to the applications. What is the Lagrange's mean value theorem? We are given a function f such that f is continuous on closed interval ab and differentiable in open interval ab. Then you can find a c in between a and b for which f dash c equal to fb minus fa by b minus a holds, right? So if a function is given, then we will check the differentiability and continuity of the function, right? If it is differentiable and continuous on the given interval, then it is eligible to satisfy the conclusion of the Lagrange's mean value theorem, right? Now let us solve a problem related to this. Now we are given that if 0 less than a less than b less than 1, prove that b minus a by 1 plus b square is less than tan inverse b minus tan inverse a less than b minus a by 1 plus a square. And hence prove that this one, pi by 4 plus 3 by 25 less than tan inverse 4 by 3 less than pi by 4 plus 1 by 6. So this is an application of Lagrange's mean value theorem, right? So whenever you are given to prove this kind of inequality, we have to consider the function as f of x is equal to tan inverse x. Tan inverse x. So if you have tan inverse b minus tan inverse a in the middle, you take tan inverse x. Sin inverse b minus sin inverse a, then sin inverse x or cos inverse x, right? Accordingly, we consider the function. So in the interval, x belonging to the interval ab. Now we'll find the derivative of f. The derivative of tan inverse x is 1 by 1 plus x square. And x is belonging to closed interval ab. And what is about a and b? They are lying in between 0 and 1. Because they lie between 0 and 1 and the denominator is equal to 0. If the denominator is equal to 1 plus x square, you make it equal to 0, x becomes complex roots, right? You will get complex roots for this equation. 1 plus x square equal to 0. And in the real line, you don't have the roots plus or minus I. Therefore, the denominator is never 0 for any point in between 0 and 1. For any point, in fact, on the right real line. Therefore, f dash is well defined. This implies f dash is well defined. Well defined in the interval AB. F dash is well defined means what? F is differentiable. So f is differentiable in closed interval AB. But open interval AB is enough for us. We have more than that. So differentiability implies continuity. We know that differentiability, if f is a function that is differentiable, then it should be continuous also on the same domain. So this implies f is continuous. F is continuous on the same domain AB, interval AB. Now, f is eligible for applying Lagrange's mean value theorem, right? Because it is satisfying the conditions of Lagrange's mean value theorem that it is differentiable and continuous. Now we can apply Lagrange's mean value theorem and have this conclusion. That means you can find by Lagrange's mean value theorem there exists a c in between a and b, that means in the open interval a and b, such that f dash c is equal to fb minus fa by b minus a. fb minus fa by b minus a. But what is f dash c? F dash x is 1 by 1 plus x square. F dash x is 1 by 1 plus x square. Therefore, f dash c is 1 by 1 plus c square is equal to fb minus fa by b minus a. Right? Now, this kind of problems, whenever you need to solve this kind of problems, we always start it with a less than c less than b consider A less than C less than B. Because C lies in between A and B, we can write A less than C less than B. This implies what we have to get in the middle term is 1 by 1 plus C square. That is F dash C. So 1 by 1 plus C square we should get in the middle. For that, what we have to do? We have to square. You will get A square less than C square less than B square. And then you have to add 1 plus A square less than 1 plus C square less than 1 plus B square. And you need to take the reciprocal. We need to get 1 by 1 plus C square. Here you have only 1 plus C square by 1. Right. Therefore, you take the reciprocal. 1 by 1 plus A square. And the most important point here is whenever you multiply an inequality by negative quantity or you take the reciprocal. If it is A by B greater than C by D, then you take the reciprocal B by A less than D by C. So when you take the reciprocal, the inequality gets reversed. So this less than becomes greater than. Greater than 1 by 1 plus C square greater than 1 by 1 plus B square. Now we can also write this as 1 by 1 plus B square. This is in the descending order. I am writing it in the ascending order. 1 by 1 plus B square less than 1 by 1 plus C square less than 1 by 1 plus A square. So you have 1 by 1 plus C square in the middle. There you can replace 1 by 1 plus C square by this thing. Now we write 1 by 1 plus B square is less than FB minus FA by B minus A less than 1 by 1 plus A square. So this implies you multiply the entire inequality by B minus A, right? Because A is less than B, B is greater than A, both are same, right? Then what is B minus A? B minus A is a positive quantity. So you multiply with a positive quantity, inequality doesn't change. Therefore, it is B minus A by 1 plus B square. I am multiplying entire inequality by B minus A. Then here B minus A gets cancelled. Then it is FB minus FA less than B minus A by 1 plus A square. But, so this is the result. And what is f of x? F of x is tan inverse x. Tan inverse x. Therefore, what is f of b? F of b is tan inverse b minus tan inverse a less than b minus a by 1 plus a square. So this is the result we need to prove, right? We have proved it. Now you need to deduce this result inequality from this. For that, what we have to do, in place of tan inverse b, you have tan inverse 4 by 3. So in place of minus tan inverse a, nothing is there, but you have pi by 4 on both the sides, right? So this second term tan inverse a is always related to this pi by 4. In some problems, you will have sin inverse a here, pi by 6 here, cos inverse a here, pi by 3 here. So these two are always related. So you equate these two, tan inverse a equal to pi by 4. Tan inverse a equal to pi by 4. That means what happens? A equal to tan pi by 4. Tan pi by 4 is tan 45 1. So you have to take a equal to 1. So put a equal to 1 and what should be taken as b, because we need tan inverse 4 by 3 here, you take b equal to 4 by 3. So b equal to 4 by 3. Then what happens? 4 by 3 minus 1 by 1 plus 4 by 3 whole square less than tan inverse 4 by 3 minus tan inverse 1 less than 4 by 3 minus 1 by 1 plus 1 square, because a is 1, right? Now, so this 4 by 3 minus 1 is 1 by 3. So in numerator is 1 by 3 by, the denominator you have 1 plus 16 by 9. If you take the LCM, you will get 25 by 9. So it is 25 by 9 in the denominator, less than tan inverse 4 by 3 minus, what is tan inverse 1? It is, tan inverse 1 is pi by 4 because a is 1, right? So minus pi by 4 less than, numerator is again 1 by 3 because it is b minus a, again 1 by 3, denominator is 2. It is 2, I write it as 2 by 1. Then it is, in this particular term, it is 1 by 3 into 9 by 25. 9 by 25. So it is 3 by 25. 3 by 25 less than tan inverse 4 by 3 less minus pi by 4 less than, here it is 1 by 3 into 1 by 2. So 1 by 6. Now adding pi by 4 throughout, you will get pi by 4 plus 3 by 25 less than tan inverse 4 by 3. Here pi by 4 and pi by 4 minus pi by 4 gets cancelled. So less than pi by 4 plus 1 by 6. And this is the required result we are asked to prove. This thing, right? So this is what we have proved. This is very important problem in the examination point of view. Applications of Lagrange's mean value theorem. Thank you so much. If you have not subscribed yet, please subscribe to my channel. Like this video, share it with your friends and classmates. Comment your feedback. If you want to learn any new concept, please put it in the comment section. Thank you.